There is a mountain range in central Florida that does not appear on any geological survey of the state. It rises from the flat scrubland of Polk and Hillsborough and Manatee counties in gray-white slopes, some peaks climbing more than 200 feet above the surrounding plain, and if you press your hand against the surface on a warm afternoon, you will feel something that the official signage, where any signage exists at all, will not explain. A faint, persistent heat that has nothing to do with the sun. The slopes leach a pale, acidic runoff into the surrounding flatlands. The groundwater nearby carries traces of substances the state has been measuring and quietly arguing about for decades. From the highway you would not know. There are no warning signs visible at distance, no roadside markers identifying what you are looking at, no historical plaques describing what these structures are or what they contain. They simply exist as they have existed for more than a century, enormous and grey and permanent, and almost nobody outside the industry that built them has ever been told their full story. These are not geological formations. They are not landfills in any conventional sense. They are the physical residue of a system that fed the modern world. And they are, in the precise technical language of federal environmental regulation, classified as naturally occurring radioactive material, NORM, mildly radioactive, permanently, with no feasible remediation pathway, no decommissioning timeline, and no end date on the horizon visible in any current state or federal planning document. The machine that made them worked perfectly. That, it turns out, was the problem. To understand how these mountains appeared and why almost nobody was told what was inside them, you have to go back to 1881 and one geologist standing in a central Florida field who had no idea what he was about to start. Captain J. Francis LeBaron was a United States Army Corps of Engineers officer conducting a survey of the Peace River Basin when he first documented the unusual rock formations embedded in the sandy substrate of central Florida's Hawthorne Formation. Ancient marine sediment laid down when this land sat beneath a shallow tropical sea packed dense with the skeletal remnants of organisms that had been fixing phosphorus from the water column for millions of years. LeBaron's report, filed with the Corps in 1881, described the pebble phosphate deposits as extensive and commercially significant, a mineral resource running across an area that would later be estimated at thousands of square miles of the central Florida peninsula, sitting 30 to 50 feet below surface beneath sandy overburden, accessible by open-cast mining with the heavy mechanical equipment of the era, at costs that made the enterprise immediately attractive to industrial capital. Within months of the survey's circulation, land speculators were filing mineral rights claims across Polk County. Within a decade, the first commercial mining operations were producing tonnage. Something about the speed of that transition is worth pausing on. LeBaron identified a mineral and American industrial capital identified an opportunity, and the gap between those two events was measured in months, not years. The rock that would define central Florida's economy for the next 140 years was in the ground at scale, and the ground was, by the standards of the Gilded Age, extraordinarily cheap. No one, in any document from that era, asked what else was in the rock. The question did not occur to anyone. It would not occur to anyone for a very long time. What made phosphate commercially vital in 1881 was a global agricultural crisis that modern audiences rarely understand in its full severity. The great farmlands of the eastern United States had been under continuous cultivation since the colonial period, and by the late 19th century, soil depletion had reached a critical threshold. Crop yields were declining. Farming communities that had sustained themselves for generations were watching their land fail. European agricultural chemists, led most prominently by Justus von Liebig in Germany decades earlier, had identified phosphorus as one of the three essential macronutrients for plant growth, alongside nitrogen and potassium, and had demonstrated that depleted soils could be restored with phosphate fertilizer. The problem was supply. The primary sources of concentrated phosphate at the time were Peruvian guano islands, rapidly exhausting, and European rock deposits, expensive to import. When LeBaron's survey confirmed that Central Florida sat atop one of the largest high-grade phosphate deposits ever identified, the strategic importance was immediate and enormous. Florida phosphate was not a luxury commodity. It was the answer to a food security crisis. This is the first thing you need to understand about what was built in Polk County over the following decades. It was built in response to genuine human need by people who believed, with complete sincerity, that they were solving one of civilization's most pressing problems. The irony that waits at the end of this story is not that they were wrong about phosphate's value. They were entirely right. The irony is that the mineral they pulled from the ground to feed the world carried something else inside it, something that would take over a century to fully account for, and that no amount of accounting has yet resolved. The chemistry that converted raw phosphate rock into usable fertilizer had been developed in European laboratories across the mid-19th century, and the process that became industrially dominant was known as the wet process. Phosphate rock crushed and mixed with concentrated sulfuric acid, which dissolved the calcium phosphate and liberated the phosphoric acid needed for fertilizer production. The reaction was efficient. It was also, from the perspective of what it left behind, extraordinarily productive in the worst possible sense. For every ton of phosphoric acid produced, the wet process reaction generated roughly 5 tons of calcium sulfate dihydrate, a white, chalky solid that the industry came to call phosphogypsum. The first Florida processing plants, constructed in Polk County in the late 1880s and early 1900s by Northern Industrial Enterprises moving capital into the newly opened territory, generated phosphogypsum from the first day they operated. The question of what to do with it was answered quickly, pragmatically, and with no apparent awareness of long-term consequence. Pipe the slurry to a nearby low-lying area, let it settle and dry, and build the waste pile higher as production continued. The stack, in the language of the industry, was the solution. It was cheap. It required no external infrastructure. It could be expanded indefinitely as long as land was available. And in Central Florida in 1890, land was available in quantities that made the question of eventual limits seem entirely theoretical. The waste ratio was locked in from the beginning, 5 tons of gypsum for every ton of product. And no one in the early industrial record described this ratio as a problem. It was simply the arithmetic of the process. The process was the answer to an urgent problem. Therefore, the arithmetic was acceptable. That reasoning would hold, essentially unchallenged, for the better part of a century. By 1900, Florida's phosphate industry was the largest in the world. By the mid-20th century, the United States was producing more than 30 million tons of phosphate rock per year, with Florida accounting for the dominant share of national output and the United States supplying roughly 75% of the world's phosphate fertilizer at peak production. The names that drove this expansion, Armour Fertilizer Works, International Minerals and Chemical Corporation, American Cyanamid, were among the largest industrial enterprises in the country. They operated in Polk County and the surrounding region as a kind of sovereign industrial territory. Their own railheads, their own company towns, their own power infrastructure, their own relationships with state government that were less regulatory than collaborative. The stacks grew. Every year, the phosphogypsum output of Florida's wet process plants added to the accumulation. The green revolution of the mid-20th century, Norman Borlaug's high-yield wheat varieties, the transformation of global agriculture that is credited with preventing mass famine across Asia and Latin America, ran on synthetic fertilizer. Synthetic fertilizer ran on phosphoric acid. Phosphoric acid ran on Florida rock. The mountains in Polk County were growing taller every year that the world was being fed, and the world was being fed at a scale that no previous generation had imagined possible. And the connection between those two facts was not something that appeared in any public discussion of the Green Revolution's achievements. A single integrated phosphate complex of the 1950s was an organism of extraordinary mechanical coherence. The dragline cranes that worked the open-cast mines were among the largest mobile land machines ever built, their buckets holding 40 to 80 cubic yards of earth per pass, moving through the sandy overburden with a slow, rhythmic inevitability that local residents described as feeling like a permanent low earthquake in the ground beneath their feet. The stripped phosphate matrix was fed into a slurry of water and pumped by pipeline, pipes running 2 feet in diameter across miles of flat terrain, to the processing facility, where the wet process acid plant received it. The acid plant itself was a landscape of reaction vessels and heat exchangers and crystallizer tanks, hot with the exothermic chemistry of sulfuric acid-meeting calcium phosphate, filled with a low hissing that workers described as the plant's constant breath. From the acid plant, the phosphogypsum slurry moved by its own pipelines to the stack, where it was discharged at the crest and allowed to flow down the slope, depositing new layers of grey-white solid as the water drained away. The stack grew from the center outward and upward simultaneously, self-building, automatic, requiring no particular human decision for each additional ton deposited, no architectural plan, no engineering review, no public notification. Only the steady arithmetic of production ratios multiplied by the volume of ore being mined. Inspection reports filed with Florida state regulators in the post-war decades describe the operations in language that is entirely technical and entirely satisfied. Production figures, stack acreage, pipeline maintenance intervals. Nothing in the routine regulatory record of this period suggests that anyone in authority was asking a different set of questions. The stack was never finished. It was always in the act of becoming. Here is what no one in the regulatory record of the early and mid-20th century was measuring. Phosphate rock, the Hawthorne Formation ore that LeBaron had surveyed in 1881, contains naturally occurring concentrations of uranium and radium, incorporated into the crystal structure of the apatite mineral during its marine sedimentary formation. The uranium content of Florida phosphate ore typically runs between 15 and 50 picocuries per gram. The radium-226 content runs between 20 and 30 picocuries per gram. These are not large numbers in absolute terms. They are not numbers that would cause immediate harm to someone handling the ore. But they are numbers that become significant at industrial scale, and they are numbers that behave in a specific way when the wet process chemistry is applied to the ore. The Atomic Energy Commission conducted industrial surveys of naturally occurring radioactive materials in the post-war period, and public health researchers were aware in a general sense that phosphate operations involved elevated radiation exposure compared to background levels. The framework that emerged from these assessments was the concept of naturally occurring radioactive material, NORM, a regulatory category that classified radioactive contamination originating in geological formations as categorically distinct from manufactured radioactive waste, and therefore exempt from the major federal radiation control statutes that had been built around the nuclear industry. If it came from the ground, the regulatory logic held it was natural, and if it was natural, it was not a hazard in the same sense as a product of human nuclear technology. The rock had always been that way. Workers had been living near it for decades. The pattern suggests, in retrospect, that the category was created at least partly because the alternative, classifying all NORM-contaminated industrial waste as regulated radioactive material, would have required confronting an accumulation problem of staggering scale. It was not yet someone's problem. It would remain not someone's problem for a surprisingly long time until the mathematics of the accumulation made that position untenable. The first formal scientific warnings about phosphogypsum radiation appeared in the academic literature in the late 1960s and through the 1970s as Florida's university research community began measuring radon emanation from the growing stacks. Radon-222 is a colorless, odorless gas produced by the radioactive decay of radium-226, and it is the mechanism by which phosphogypsum's radioactivity becomes a public health concern. Radon diffuses through the gypsum surface and disperses into the surrounding air where, if inhaled, its decay products deposit in lung tissue and deliver a localized radiation dose. University studies and early EPA regional assessments measured radon emission rates from Florida phosphogypsum stacks and found them substantially elevated above background, by some measures roughly 26 times background radiation levels at the stack surface, with occupational exposure data for workers who spent extended time on active stacks, suggesting cumulative doses that were not trivial, but that the industry consistently argued fell within acceptable industrial parameters. The industry response to these early studies followed a predictable institutional logic: challenge the methodology, emphasize the natural origin of the radioactivity, and note that workers had been present in these environments for decades without documented acute effects. The studies were not secret. They were published. They were available to any regulator or legislator who looked for them. The numbers were simply not yet attached to a regulatory obligation. And so they remained in the academic literature, accumulating alongside the stacks themselves, while the stacks continued to grow. By the early 1980s, estimates of total accumulated phosphogypsum in the United States had reached into the hundreds of millions of tons, with Florida's share dominant. The scale of the problem was becoming impossible to ignore, not because something had failed, but because something had worked too well for too long. This is where the second twist arrives, and it is the one that most fundamentally shapes everything that follows. When the Environmental Protection Agency conducted its systematic assessment of phosphogypsum radiation in the early 1980s, documented in technical reports including EPA 520/1-85-010 and subsequent regulatory analyses. What the agency's scientists found was not a flaw in the wet process system. What they found was a consequence of the system's excellence. The wet process acid plant had been designed and continuously optimized over decades to maximize the extraction of phosphate from the ore, to pull as much phosphoric acid as possible from each ton of rock, leaving behind a waste stream as chemically depleted of product value as achievable. The process achieved extraction efficiencies of 93 to 95%. This was a genuine engineering achievement, and it meant that 80 to 90% of the original ore's radioactivity, the uranium, the radium-226, the material that had been distributed through the rock matrix, was now concentrated in the phosphogypsum waste stream, not in the fertilizer product. The cleaner the product, the hotter the waste. The more efficiently the chemistry worked, the more radioactivity was consolidated into the one stream that had nowhere to go. 1 billion tons of that stream, by some estimates, already existed. The better the system had worked, the worse the problem had become. That equation had been true since the first acid plant opened in Polk County, and no one had described it in those terms. And by the time someone did, the accumulation was essentially irreversible at any practical economic scale. The regulatory response to this assessment unfolded across the late 1980s and into 1992, when the EPA finalized a rule under the National Emission Standards for Hazardous Air Pollutants, codified at 40 CFR Part 61 Subpart R, that addressed phosphogypsum disposition. The rule established a threshold of 10 picocuries per gram of radium-226 as the boundary below which phosphogypsum might be used in agriculture or construction. Essentially, all Florida phosphogypsum exceeded this threshold. The rule therefore prohibited the reuse, redistribution, or repurposing of the accumulated stacks in any application where human exposure could occur. The stacks could not be used as road base, they could not be used as agricultural amendment. They could not be sold, processed, or moved for any commercial purpose. They were to remain where they were, managed in place, monitored for liner integrity, measured for radon output, and maintained indefinitely. This is the third twist, and it is the one that closes the trap completely. The investigation had been thorough, the measurement had been precise. The regulation had been drafted carefully and enforced consistently. And the result of all that rigor was not a solution. The result was the official, legal, permanent preservation of the problem. The EPA had measured the stacks with precision and then, by prohibiting any reuse, had ensured that the stacks would remain exactly where they were, growing no larger but shrinking no smaller, for an indeterminate future measured not in years but in geological time. The documentation had become the end point. The regulation did not solve the problem, it preserved it. Sinkhole collapses at phosphate processing sites in Polk County had been documented as early as 1994, when subsurface dissolution events opened voids beneath active stacks, releasing contaminated water into the Floridan aquifer. But it was in April 2021 that the consequences of the preservation framework became visible in a way that was impossible for the general public to ignore. The Piney Point Phosphogypsum facility in Manatee County, Florida, a legacy site from the Mulberry Corporation's operations that had passed through bankruptcy and ownership changes and regulatory disputes over several decades, experienced a failure in its liner system. The stack contained hundreds of millions of gallons of process wastewater, phosphoric acid plant effluent carrying elevated concentrations of nitrogen, phosphorus, and naturally occurring radioactive materials. Florida Governor Ron DeSantis declared a state of emergency. Manatee County ordered the evacuation of residents in the vicinity. State engineers calculated that an uncontrolled liner failure could release a wave of contaminated water sufficient to inundate nearby roads and communities. The decision was made to conduct a controlled discharge. Approximately 215 million gallons of treated process wastewater were released into Tampa Bay over several weeks. The nitrogen load from that discharge contributed to a significant algal bloom in Tampa Bay, damaging seagrass beds that had been recovering from previous degradation events. Fish kills were reported across the bay. Florida DEP Secretary Sean Hamilton oversaw the emergency response, and the state's communications during the crisis were careful to emphasize that the discharged water had been treated and that radiation levels in the discharge were within acceptable parameters. Something about that framing is worth examining. The stack had been on regulators' active concern list for years. The liner had been monitored, the wastewater had been measured, the management plan had been in place. Management had simply ended, not through negligence in the immediate crisis, but through the longer institutional failure of a regulatory framework that classified the problem as manageable without providing a mechanism to actually manage it toward resolution. Piney Point was not unique. Florida had, by various counts, approximately 25 active or legacy phosphogypsum stacks at various stages of operational status, closure, and abandonment. Some were associated with companies that remained solvent and legally responsible. Others had passed through bankruptcy proceedings that severed the connection between the waste and any identifiable responsible party. Environmental advocacy organizations, including the Public Employees for Environmental Responsibility, had documented the orphaned stack problem in reports filed with state and federal regulators. Sites where the liability chain had broken, where the closure plan existed on paper, but the funding for its execution had evaporated with the company that generated the waste. University of South Florida researchers working in the region had measured radon emissions from legacy sites and found that the decay chemistry was proceeding exactly as the physics predicted, indifferent to the commercial status of the facility or the solvency of its former operator. The stacks did not require an operator to continue functioning. Rainwater infiltrated the surface. The chemistry proceeded. The radon diffused upward. A machine running with no operator is not stopped. It simply runs until it cannot. The most recent attempt to escape this trap came from an unexpected direction. Beginning around 2020, the phosphate industry and its political allies in Florida's congressional delegation began pushing for an amendment to the EPA's 1992 phosphogypsum rule that would permit the use of the material as aggregate in road construction. The economic logic was straightforward. Florida maintains thousands of miles of road-based aggregate has significant cost, and there was a billion-ton supply of material with the right physical properties sitting in stacks across the state. The Trump administration EPA moved toward accommodating this argument, proposing a rule revision that would have allowed phosphogypsum to be used in federally funded highway projects as a pilot program. Scientists from the EPA's own radiation programs, along with researchers from the academic community, objected on specific technical grounds. Radon emissions from road surfaces constructed with phosphogypsum aggregate would expose road workers and nearby residents to elevated radiation doses over time. The Biden administration reversed course in 2021, withdrawing the proposed rule change and restoring the original prohibition. The stacks remained frozen. The moment someone found a way to use the waste, someone else proved it was still dangerous. The economic incentive to solve the problem disappeared again, and the problem remained exactly where it had been since 1992, legally defined, precisely measured, officially permanent. The phosphate empire that created these mountains is itself now in decline, and the decline has a specific economic cause. Morocco's office Chérifien des Phosphates, OCP Group, controls approximately 70% of the world's known phosphate reserves, concentrated in the Western Sahara and the broader Moroccan phosphate basin. The Moroccan reserve base is so large and OCP's production capacity so substantial that Florida's increasingly expensive, increasingly regulated, increasingly deep mining operations cannot compete on price in most global markets. Florida phosphate production, which once dominated global supply, has contracted significantly. Plants that operated for decades in Polk County and Hillsborough County have closed. The draglines have stopped, the slurry pipelines went dry, The acid plants have been demolished or left to rust, and in some cases, the plant sites have been converted to other uses while the adjacent stacks remain, unchanged, permanent, still the tallest features in a flat landscape. The last operating legacy facilities continue under Mosaic Company's management, and their own future is subject to the same economic pressures. The empire is ending, the mountains are not. Radium-226 has a half-life of 1,600 years. This is not a metaphor. It is a physical constant, a property of the nucleus, immune to chemistry and economics and regulatory frameworks and political administrations. The phosphogypsum stacks in Polk County and Manatee County and Hillsborough County will still be measurably radioactive in the year 3626. The people who built the first acid plant in the 1890s, the engineers, the investors, the plant managers who woke at dawn in company towns at the edge of the Florida scrub and walked to a facility producing something the world needed, who solved the great agricultural crisis of their era with a chemistry that worked, who generated the first pile of grey-white waste and directed the first slurry pipe toward the first low-lying field, could not have known this. They solved the problem in front of them. The problem behind the problem. The radium-226 in the rock, the concentration effect of the wet process, the billion-ton arithmetic of 5 tons of waste per ton of product, was not visible to them and would not have been visible to anyone for decades. Something about that sequence of facts is worth sitting with quietly. The stack is still out there in the flat scrubland off the highway in Polk County, grey and enormous and faintly warm. The dragline is still. The slurry pipe is dry. The acid plant is a ruin. But the stack, taller in profile against the Florida sky than it was on the day the plant closed, is still, in the technical sense, working. Rainwater moves through it daily. The chemistry has not stopped. The radium decays on its fixed schedule. The radon diffuses upward into the air above the flatlands, and the question that no institution has fully answered, not the EPA, not the state of Florida, not the companies that built these structures, not the regulatory frameworks that preserved them in place, is the question that sits at the bottom of every assessment and every emergency response and every rule-making docket. Not what to measure, but what to do. They built a system to feed the world. The world moved on. The mountains stayed.